So if you've got here, you've made it to part 3. Congratulations. Hope you understood all of the questions in the previous 2 videos that we've gone over. This is the final one. This basically has appeared once in the last 10 years. So could happen, probably won't. But if you want to prepare for UA Star ones, you've got to go over every single type of question. So this question, student requires a buffer, gives you a pH. So what do you do with the pH? You should be saying to the video right now, what do you do with the pH? You get the H+ concentration, okay? Deduce the acid required by the student to prepare the buffer. So we're going to give you some acids in a minute. Calculate the relative concentration. So it's a ratio thing between the salt and the acid that you need to calculate, which is the same as in video 2 where we did it there, okay? So let's put this to the side, and here's your acids that you have got. You've got this, and you've got pKa's. Now there's a little rule, okay, that we're going to start to talk about when it comes to this type of question. And that rule basically is if you have got a pKa value and it asks you to choose an acid to make the buffer out of, then you choose the acid with the pKa value closest to the pH you want. So what's the pH we want? Let's put it down here. The pH, let's get rid of all of that stuff. We just want that pH. So we want that pH. If we want that pH, which one's closer? Okay, and the one that's closer is going to be the one that's closer to 4.5, which is 4.76. So remember, you're choosing the acid for your buffer that's closest to the pH required, so it's got to be this one. Okay, so basically we're going to go for acetic acid. So let's put acetic acid in and start using the equation. So we've got this equation from a previous video, and you can see that this equation, okay, got our ratio. So if we've got a Ka and we've got a H+, we'll know the ratio between the salt and the HA. So remember, pKa can be converted to Ka, and your pH that you want can be converted to H+. So here is your pH being converted to H+. Here's your pKa being converted to Ka. So we've got these 2 values which can substitute in there and there. Okay, so if they can substitute in there and there, we will know the ratio here. So let's do the next part then, shall we? Okay. There we go. So we've just cut the table, and then you've got your pKa value at the bottom. All right, so then we're going to do is put it into the equation. So first of all, we're using the H+ 10 to the minus pH. So we've got the pH from down there, 4.5. Again, if you think you can do it, stop the video, do it. Don't watch it. It can be very boring watching a video. Make sure you're doing something during the video. Okay, Ka, 10 to the minus pKa, and there's your values. And then all you do is take this, rearrange it so it looks like that one up there. Okay, all we're doing is dividing by the H+. Okay, and then you put it into the equation, and your ratio should be 0.55. Now remember, if you're quoting it as a ratio, that's 0.55 over 1, okay? So 0.55 over 1. And that is how you do and get the ratio. Now, I want to show you just briefly why you want a ratio like this, why this is the correct acid, for example. The reason it is because the ratio is as close to 1 to 1 as possible. So what does that mean? So we've answered the question, but let's go on further just to say why are we doing this? Why do we pick the pKa, the acid with the pKa closest to the pH? It will give you a 1 to 1, as close to 1 to 1 ratio of the salt to the acid. So let's show you what would happen if you didn't do that. So the acetic acid is that ratio. The ratio of the citric acid is 23.44 over 1. You see, it's massively in favour of the salt. So if that's the case, let's just put it in the case of acetic acid, not citric acid. Okay, and we know full well if we add OH-, okay, if we add some alkali, it's going to react with the H+. This H+ is going to go down, and so the equilibrium will go over to the right. So if we add OH-, the equilibrium will go to the right to put the H+ back up to its level so the pH remains the same. Now, if we then put in H+, okay, so we've added H+, okay, the A- will react with it to go back that way, which means equilibrium will go to the left if you add H+. So equilibrium goes to the right if you add OH-, equilibrium goes to the left if you add H+. Okay, so if that's the case, we need a lot of acid and we need a lot of A-. because on this one, we're going to use up the HHA because we're going to go to the right. It's going to use that up. Okay, and on this one, we're going to use up the A- because it's going to go in that direction. Now, that means if you've got a 1-to-1 ratio, then you can add acid or alkali and it'll still work perfectly well. Okay, so acid or alkali still work perfectly well because you've got a 1-to-1 ratio of each one-ish. This one has got a lot of salt, which means it'll be really, really good if you add H+, because lots of salt to react with the H+, get the H+ back down again, okay, and you'll be absolutely fine and it'll work. But as soon as I start adding the OH-, the OH- takes away the H+, and we haven't got a lot of HA to fill that H+ back in. So this buffer wouldn't be good for acid and alkali, okay, but this one would be good for acid and alkali. So the question is, why do you pick the acid that has the pKa closest to the pH? You pick that acid so that it works well with acids and well with alkalis. And that is our final question of 3 videos on buffer calculations, which are the most complicated calculations you'll probably do in your entire A-levels. Okay, I hope they made sense, and get on practicing. Okay, I hope, and if you did enjoy the video, please subscribe and please share. Okay, it takes a lot of time to make these videos, and I really appreciate it if you share them as much as possible. Thank you.